Hello everyone, this is Scott from Pivot. Want to say hello and also share one of our phases, the pentafluorophenol phase, as well as the pentafluorophenol and C18 phase as well, or PFP and PFP&C18 as many of you know. So what I'm going to do is I'm going to jump right into some applications, and we'll use these applications to show some of the advantages of these phases and how they compare to a C18 column. And then at the end, we'll come back to these slides here. So I'm going to move down here and jump right into the applications. Let's look at separation of xanthines. And so at the top here, you'll see the SunShell C18 column. And this is a core shell column, and these PFP columns do come in both core shell as well as fully porous material, which we'll highlight later. But for the comparison right now, we'll look at a SunShell C18 as well as a PFP column, and it's a 2.6 micron with a 2.1 millimeter ID and 150 millimeter length. And the mobile phase is methanol and water, and we will also look at phosphate buffers later. But looking at the top two chromatograms, you will see that the PFP column retains xanthines better than a SunShell C18 column. And then if you hone in a little more on peak number 3, caffeine, you can see that the retention time for something like caffeine is longer with a SunShell PFP column. And then if you look at the phosphate, so if you add a phosphate buffer at the bottom two, so in one case there's a 20 millimolars of a phosphate buffer, and then the one on the bottom is a 50 millimolar of a phosphate buffer, you can see that the retention time is longer in these cases. Now, what about retention comparison of cation between C18 and PFP phases? And I'm going to look at some notes here. I'll refer to these to help keep this short presentation moving as well. And so we're going to compare two columns here, the SunShell C18 as well as the SunShell PFP column again. In this case, we'll be doing, again, 2.6 micron and 4.6 millimeter ID by 150 length. The mobile phase is acetyl nitrile and a 10 millimolar of a phosphate buffer, pH 7. And so these samples are protonated under a neutral pH. And so the mobile phase, it has an 80% acetyl nitrile. And so this is a very high concentration of an organic solvent. And so if you look over here at the top, you have the SunShell C18. You can see that it does not retain these basic compounds very well. But the SunShell PFP column on the bottom does retain these basic compounds quite well. And so what's some of the reasoning for this? And so it's the dipole-dipole interaction is working on the PFP phase. So the deflection of electron to fluorine makes cation a protonated basic compound which retains on a stationary phase. And so this is an electrostatic interaction and not a cation exchange. And as a result, there's little effect of residual silanol groups on the PFP phase as well. So what about separation of isomers of cresol? And so this slide here, again, we're looking at SunShell C18 as well as the SunShell PFP columns here. And so we're looking with the mobile phase of methanol and water here as well. And so at the top, you can see that the SunShell C18 is able to separate the ortho cresol, but not as much the para and the meta cresol. On the bottom, you can see the SunShell PFP column, and that is able to separate the para cresol, the meta cresol, and the ortho cresol quite well. Just as a side note though, so if a crown ether is added to the mobile phase, the C18 would be able to separate all three. Again, the paracresol, the metacresol, and the orthocresol. Now, what about separation of components of explosives? So looking at this here, we'll look at this on the left. We have methanol and water. On the right, we have acetonitrile and water as the mobile phase, and we break down the various columns as well. And you're going to see here the peak number 1, you'll see a 1,3-dinitrobenzene, and peak number 2, which we'll also highlight, is the 1,3,5-trinitrobenzene. And so a nitro group shows pi-pi electron interactions. And so furthermore, a nitro group makes hydrophobicity decrease. So again, referring to this, so peak number 2, 1,3,5-trinitrobenzene showed shorter retention time than 1,3-dinitrobenzene when a C18 column is used. So we're looking at the top, the SunShell C18 column, and when methanol and water is used as a mobile phase. So the shorter the retention time, the lower the hydrophobicity of a compound, particularly when methanol and water is used as a mobile phase. Let's go down a little bit to the bottom. We'll see the SunShell phenol column. And so if you look at this, the elution order is a little different to that of the C18 column. The phenol phase shows a pi-pi electron interaction. So the 1,3,5-trinitrobenzene, peak number 2, retains larger than 1,3-dinitrobenzene. And the reason for this is that the nitro groups are different between these two, peak number 1 and peak number 2. Again, 1,3-dinitrobenzene, and peak number 2, 1,3,5-trinitrobenzene. So how about the PFP column? So looking at this, if you see the dilution order is the same as the C18 column. And this means that the PFP has very little pi-pi electron interaction, or actually pretty much none in comparison. So this is just giving some perspective. Now, what about separation of fluorobenzene? Now what we're going to do here is we're bringing in the SunShell PFP and C18 column as well. And so the mobile phase is a methanol and water. And so looking at peak number 1 is benzene, and peak number 2 is fluorobenzene. As you can see, the C18 is unable to separate the benzene and fluorobenzene very well. However, the SunShell PFP and the SunShell PFP C18 are able to do this separation. Now, the only difference is that the PFP C18 has a longer retention time. Now, what about stability of looking now? We're going to look at these two columns, the stability of PFP and PFP C18 column. So due to the increased hydrophobicity of the surface, look at in reference to the PFP and C18 column, the durability of this PFP and C18 column is approximately 3 times that of a conventional PFP. And so this is important because PFP columns are not known to be the most stable. So this is something to look at. Now, what about comparison of retention times for highly polar compounds? As we'll see here, and we're going to refer to peak number 1, epinephrine, and then peak number 2, levodopa. And so the separation of highly polar compounds is a little different. And so in this case, you'll see that we're also using as a mobile phase 12.5 millimolars of ammonium formate as well. And so in this case, the epinephrine was highly polar. And so in this case, the PFP column showed much longer retention time than that of the PFP and C18 column. Also to note, we're using the fully porous columns, the Sunniest columns for this comparison. Now finally, what about separation of isomers like cis and trans stilbene? And on the left, we have methanol and water. To the right, we have acetylnitrile and water. And we're looking at C18, C30, phenol, biphenyl, PFP and C18, as well as the PFP column. And if you look on both sides, you can see that the PFP and C18 column has the best separation and the largest separation factor. Just something to look at, just showing some comparisons here. Now going back to the end here and just in summarizing, we just wanted to show you that right now one of the newer columns that we have is the PFP and C18 column, which we highlighted as well. And so we're taking basically the C18 hydrophobicity and the PFP separation to provide increased retention and improved durability. And then we also have a complete line here that shows some of the columns we have, both in the core shell as well as with the fully porous material as well. If you have any questions regarding this and other columns and other applications, please do let us know. Thank you so much.